So I'm here to say just a little bit about the Chambliss Award. The Chambliss Faculty Research Award started in 2004, and as most of you, probably all of you know, it came from a gift from Dr. Carlson Chambliss, who is a professor emeritus, and he was from the Department of Astronomy. Physical sciences, but his area is astronomy. I'll get it right eventually. And he was here from 1970 to 2003. So being mathematical, I would say that's 33 years, which is quite impressive. And there we have topped out on my degree of mathematicalness. This award recognizes the very highest achievement in research and scholarship. So each year up to 2 awards can be given, and the award can only be received one time in a faculty person's career. The award has 3 components. There is a gold-plated medal that was designed by Dr. Chambliss with the awardee's name engraved on it, a certificate of recognition, and a cash award, because cash always fits. And we're very grateful that Dr. Chambliss's generosity allows us to present these awards and that it gives us an opportunity to hear about the great research and creative activity that our faculty do. So can anybody, I can't see anybody really. So can anybody who has received this award in the past please stand so that we can give you a, yeah. And I'm sure we all send a thank you to Dr. Chambliss for his generous support of our faculty. So our first 2024 recipient is Dr. Tony Wong from the Department of Mathematics. And I'm going to turn the mic over to our Dean of Liberal Arts and Sciences, Dr. Lori McMillan, to introduce him formally.
Good afternoon, everyone. I'm super pleased to be here and honored to be able to introduce Dr. Tony Wong today. And I'm going to do a bit of a thematic introduction. Okay, so this is going to be a little bit hard to juggle, so bear with me. Dr. Wong has been with us for 11 years here at KU. And over the course of his career, he has published 28 papers in peer-reviewed journals. Of those, 17, or 61% have involved undergraduate students. So that's pretty impressive. In addition, I'm just going to talk loudly because this is way too hard. In addition, can you still hear me? Okay. He has served as reviewers for 7 different journals, and he has been senior personnel, 2 different NSF awards, totaling $1,364,188. He has also been one of the founders and chief editors of a peer-reviewed journal called Communications on Number Theory and Combinatorial Theory. The acronym is CONTACT, much easier to say. Back in 2022, Dr. Wong was really privileged to have one of his papers published in Discrete Mathematics win an Editor's Choice Award. Now, the journal is called Discrete Mathematics, which seems odd because somehow they want to publish and circulate information widely. But despite that oddness, it is a tier 1 journal, publishes about 400 papers a year. Dr. Wong's paper was one of 16 to get that Editor's Choice Award, which means it was in the top 4%. In terms of content, he publishes on, I have trouble with this word, combinatorics, I'm close, graph theory, design theory, and other topics. I'm going to leave more of the specifics to Dr. Wong to explain to you because I am only partially fluent in mathematics. So without further ado, please join me in welcoming our one and only Dr. Wong.
Yes. All right, great. Thank you, Dr. Macmillan, for the nice and great introduction. Can you hear me from the mic? Good, awesome. So today I'm going to give this talk in a very different way than I'm used to. So I'm very nervous right now. To make it more clear how it's different, usually it's just me talking and then the audience just listen. But I want to make it totally different this time, and I want more audience participation. Okay, and so to get you started, we are going to start with a pop quiz. Uh-oh. Now you would be thinking, like, why would I ever come to this talk? Like, I'm not ready for this at the very beginning. Well, I'm just kidding. It's not really a pop quiz for you. If anything, it might be a pop quiz for me. So I would like you to all take out a calculator, which is completely counter to what I'm used to do. I always ask my students, no calculator. You can do everything like 3-digit times 4-digit, like all through your head. But this time we can just break that rule and you can take out a calculator. You might have an app or something on your phone. And here is what I want you to do. Think of a 3-digit number and you can type it on your calculator. If you want, you can make it a 4-digit or 2-digit, but just roughly speaking, 3 digits. Multiply your number by this weird looking number called 387. Okay, and then you hit an equal sign. Now, what I want you to do is to read the digits of your product in any order you want. Read out loud to me, but in a moment, because I want to give you further instructions. If your product has any zeros in that, then please ignore them because zeros are just placeholders, right? And so we will ignore zeros. So for example, if you get 90,343, so 90434, whatever it is, then the zero, you just drop it and just look at the other 4 digits, okay? And furthermore, when you read out loud to me, you may hide exactly 1 digit and read the rest to me. Is that okay? So for example, if it was 9434, you can say 943, and then I would, and that is what I want, okay? All right, so is there any volunteer who would like to do that? Yes, Dr. Shapirs. So
right.
by the way, because I'm not a very audio person, I would like to actually get to a screen where I can type. And there you go. You can see my hands shaking. All right, go ahead.
4837.
Okay, 4837, huh? Is the number that you're hiding from me 8?
No.
Uh-oh. I know. Okay, is the number that you're hiding from me 5?
Yes.
Oh, okay. Whew. Any other volunteers, please? Okay. I always call it Nate. Mr. Polidoro. Yes.
My number with 1 digit hidden.
Okay. Is the number that you hide it from me 9? Okay, so kind of 1.5 out of 2 so far. Any more volunteers? Let's do 2 more. Yes, Mr. Dacko. 183. Oops, sorry. 18374. Did you say? Okay, and so that would be 4 that you hide. Okay. Anyone in front? Like, yes, please. 2168. Okay, is that a 1? Okay, cool. Let's do 1 more. Last one. Yes. 224. 1, 2, 24. Is that a 1? Cool. All right, thank you. So that's the warm up. And do you want to do 1 more? activity before we start the talk? Okay, all right. Yeah, so yes, thank you for your input. So Dr. Hodgkinson, may I invite you to give me a random number, random integer between 1 and 20.
17.
Okay, all right, 17 it is. Okay, so you see this thing on the bench here. And so now I'm going to open it. Let's see. Oh, there's another envelope. Now I'm going to open this envelope. As you can see, my hands are shaking really, really crazily. All right. And by the way, this trick is really the first time I'm doing it. I forgot the number. Is this 17? Okay, all right. Oops. So this is stuck. Okay. Because it's kind of like connected with tape. Oh, this doesn't look like 17 to me. Uh-oh. So what's going on? So what I want to do is that I'm going to the calculator online. They give more digits for the division. And so it was 17. And then I'm going to divide it by 23, just why not? And so what's the first digits that we see? It's down here, okay, if you can kind of see it. So it's 739, right? So the first couple digits is what? 739. And then 130, 130. But we are mathematicians. We are not like just satisfied with that. Maybe the things will break later. And then what? 434, 434. And then 782, 782. 608, 608. And 695. 217. Did I read something wrong? 695, 652, sorry, 652 first. As you can see, 652, and then 1. And then why do I stop there? It's because notice that this is a periodic number. So 739 will repeat here, 739. And therefore, what I gave you is the infinite precision of the decimals of the number 17 divided by 23. By the way, 17 is not chosen by me. It's just randomly chosen by Dr. Hodgkinson. But I was able to predict that the night before and put it in this envelope. All right. Whew. All right, the hardest part is now done. All right, so why can these things be possible? Actually, it's because of a field in mathematics called number theory. If we have time, we can touch on why these tricks work, but let's get into the actual heart of the talk right for now. Okay, so let's see here. Share, present, get it right. Okay. So at the beginning, before we start the entire process, I get an email asking about an abstract for this talk. And I was like, well, I can talk about all sorts of research that we are doing or some other people are doing, and they are really fun and exciting to me. But they may not be, how do I say it? Not many people in the audience may be able to appreciate that. Why? Because to be honest, it is maybe partially a fault of mathematicians not being able to popularize the field of mathematics to everybody. Like you can read on the newspaper almost every day about some breakthroughs in medical research. You can read about maybe astronomy research. Maybe we can read about like art or music or just some new creation, architectural creation, but very few articles about math research. And so maybe we can do a little better to explain what mathematics research is. So I want this talk to be a little bit less discrete in the sense. And so I'm going to decide to start with this discussion about what mathematics research is. So before I give my point of view, I just want to share with you some other points of view that I often hear from different people. Very often I hear that people say, why do you do research in math? Math is just math. I mean, they don't change. And you're right. Like, I mean, I actually this morning I saw Dr. Fernando, and I said to him, I'm going to make fun of physicists. Well, to think about it, right? I mean, physicists do their research and they work very hard to try to prove that their theory is wrong. I mean, over the years, right, they thought about, okay, maybe there's something called ether that fill the universe. And then they found, oh, that doesn't work. Maybe there's something called Bohr model for each particle where you have nice circular round shells around like the proton and I mean the nucleus, and that's not how it works. And then gradually, like it gets into quantum physics, and I was looking at it. Is that really making sense? I don't know. I mean, maybe 30 years later, they would say, oh, actually, they're all just a joke. And now I have a new theory. Who knows? All right. Well, for mathematicians, that doesn't happen. Math is always true. They never changes, right? For example, hundreds or even thousands of years ago, we have already developed this kind of like Pythagorean theorem. I believe that many of you, even you may not fully recall what it's about, but you still remember the name. Am I right? Okay, so what does it say? It's talking about right-angled triangles. And if you have a right-angled triangle, then the one leg, if you square that length, and then the other leg, you square that length and sum them up, it will be the hypotenuse squared. It's called a squared plus b squared equals c squared. Great, so that never changes. And I agree that never changes, except we don't really live on a plane, do we? We live on the Earth, and we found that the Earth is more or less spherical. Okay, so if we actually try to draw a very large right-angled triangle on the Earth and try to measure so-called the length, that gets tricky because it is no longer really a straight line between the 2 points to be called a length. It has to be something called geodesic, a very complicated math term, but just some curve, shortest length arc between points, and then we measure that length. And will that satisfy the a squared plus b squared equals c squared? And obviously not. And so we have to completely do our math completely differently and find out what works on the spherical. And there's a new field called spherical geometry because of that. And so, yeah, we have established theorem, but once you change some of the conditions, for example, from the plane to the sphere, then you have to do things completely new again. Okay, so that kind of justifies why we need to do math research. Now, another point of view is like, I actually have a story. I mean, it's not really a long story, but actually, when I was an undergraduate, I went to Cornell for a summer research program. And then I remember my wife, Jane, was with me at that time in Cornell. And then I sent her back to the airport because she's only staying for 1 week. And then I took a taxi up back to the campus. And on the way of taking that taxi, the taxi driver asked me, like, why are you here in nowhere, in the middle of nowhere? And because it's Ithaca. And I was like, oh, I'm doing research at Cornell. And he was like, oh, what kind of research? Is it like medical research or like whatever? And I was like, oh, it's math. And I was like, oh, math research. Do you try to prove 1 + 1 is equal to 2? And I was like, I was a little embarrassed. I wasn't ready for that kind of like remark. But now maybe we can answer that slightly better if I'm more experienced. I would just answer to him that basically 2, what is that? It's just a symbol to denote the concept called 1 + 1. It's just a shorthand notation. In English, we call it 2. In French, we call it deux. In Mandarin, we call it In Cantonese, we call it yi. And you can just talk about all sorts of languages and they use different symbols and they just denote a concept. It has no meaning. There's nothing for you to prove. It's just a definition of that symbol. Okay, so there's nothing to prove about this 1 + 1 = 2. However, there's still something more about this 1 + 1 = 2. For example, 1 + 1 can be equals to this symbol called 1, 0, or some people may call it 10, right? I mean, mathematicians would know why. Can I get an answer from some of you? Base 2, very good. What is base 2, by the way? Yes, binary, okay. So what 1 + 1 = 10 means what? Basically, the idea of 10 is because we have 10 fingers. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't have any more fingers. So you know what? Let's just call that a 10. We create this concept. And then that's basically one collection of 2 5s. And that's called 10. And then on top of that, it will be called 10 + 1, or some people call it 11. Now, if you don't have 5 fingers on each hand, but you only have 1 finger on each hand, okay, imagine. So now you have 1, and then you have, oh, that's 2, but at the same time, you use up all your fingers already, correct? And so you want to say, oh, I collect this 2 1s to be called 10, and then the next one will be called 1 1. Does that make sense? So that's what base 2 is doing. Now, this is not because mathematicians have too much time and just want to do this for fun. Well, actually, we do have too much time. Well, no, I'm just kidding. It is because of, right, computer science. We know that computer is using 1s and 0s, and a lot of calculations has to be done binary. So completely different calculations and arithmetic there. 1 + 1 can also equal to 0. What do I mean? Well, I'm not talking about 1 - 1. I mean 1 + 1. I really mean 1 + 1. What if 1, the first 1, stands for 1 flip of a coin? Plus means that you, on top of that, do another operation called another flip of the coin. So think about it. If you have a coin, you flip it once, and then you do another once. Isn't it like you didn't flip at all? Because you get the original configuration back, right? So 1 + 1 can be equal to 0 indeed, right? And so if you think about the operator differently, if you put it in different contexts, you can indeed get different answers. Of course, mathematicians call it modulo 2, but we won't get into that too much further. Some other people would say, oh, because actually I do meet with middle school kids a lot. Every year, Dr. Carol Watson will bring a lot of young, energetic middle school kids on campus, and I always meet with them every year. It's really exciting. And so when they talk about what mathematics is, it's like, oh, is it true that you try to find a fast way, super fast way to do calculations? I guess it's because they're doing pre-algebra, that kind of things, and so they're doing a lot of multiplication. And so they find like, oh, maybe like if you can do really fast multiplication, that's really cool. So I answer to them is like, well, actually, if you just talk about integer times integer, that is not too interesting. How about something called matrices times matrices? That's get exciting. What is a matrix? Matrix is just an array of numbers. And when you need to consider the relationship between objects, you might need to think about something called matrix multiplication. And just to put it in the slightly better perspective, very often we have networks, for example, human network or brain network between neurons, or just whatever network you can think about. And if you want to think about how many steps, or sorry, how many paths you need to you can go from one point to the other, and the most efficient way is probably to multiply matrices. And these matrices are of size billions by billions, if not more. Because we are talking about, for example, network on the internet, right? If you just type something on Google and then they pop something up, that type of network is gigantic. Neuron network is gigantic. And so if you have such a big matrix, how do you multiply fast and efficient? How do you even approximate? Because it's too clumsy to do that. And so that is indeed a very important topic for many mathematicians. In fact, I have a friend who did his PhD at Stanford, and his PhD in mathematical engineering is purely to find the fast and good way to approximate or solve some sort of a matrix inversion. Inversion is basically division. It's the analog of division in matrix world. Next. Maybe you are just solving super complicated equations, also from some of those middle school kids. And I was like, well, you know what? Actually, I see Dr. Emmerich here, and maybe he would like it, and Dr. Lee here. Differential equations, indeed, right? So heat transfer, which is the expertise of Dr. Lee, biological model, and for parasites, Dr. Emmerich's expertise. Blood flow, etc. All of these involve something called differential equations. And so how do you solve them? And how do you find a good solution to them is a big research topic. Very often, these kind of equations cannot be solved, which is very sad. They cannot be solved analytically. You cannot find an exact solution, but you can approximate them. Furthermore, sometimes not just how to solve the problem, is rather how to set up the equation is the big question. Now you look at the problem, but how do you use the knowledge of mathematics to represent that model? So all of those fall under mathematics research. Okay, so a lot of different perspective from different people about what mathematics research is. What about my take? Well, the answer is, I don't know. I mean, I have conducted mathematics research maybe for slightly over 10 years. And honestly, I don't know what mathematics research is. If you want me to give a definition, I don't know how to give it to you. I mean, just think about it. You all know what cookies are. But if I ask you to give a definition to a cookie, can you really give me a precise definition of what a cookie is? It's very hard. Very, very hard. So I kind of know what's going on, but I can't really give you a definition. I can just give you a little bit of my taste. From what I see, lots of what ifs in mathematics. For example, I just had this example earlier. What if our geometry is no longer on a plane, but on a sphere? Right? Then what if that is changed? Then how would all how the geometry will change? What if we change from base 10 to other bases? What would happen? All right. So a lot of questions is formally already done and conducted and well understood. But what if you change the condition to something else? Then what would happen? That would be totally different new math research topics. So a lot of what ifs. A lot of whys, we would like to ask why. For example, this sequence 1 + 1/2 + 1/3 + 1/4 + 1/5, etc. If you have taken calculus 1, you would know that it does not converge. But yeah, your professor told you that it doesn't converge. By the way, the name is called harmonic series. But why? So of course, knowing that it doesn't converge maybe is something that we want our students to know, but to ask or actually come up with the question, ask why doesn't it converge? That is a mathematician mind. If whatever something that is told to you, and then if you ask about why, then basically you can tell yourself, oh, actually I'm thinking like a mathematician now. Okay. Another example, you know a squared plus b squared equals c squared has a lot of solutions, but it turns out that a cubed, I just changed the power from square, the 2, into a 3. It turns out that if you keep trying and trying and trying and trying, you just cannot find positive integer solutions. But why not? It turns out that this is a special case of something called Fermat's last theorem, which took 280 years to prove. And it was recently proved, well, I mean, considering the history of the world, 1996, it was proved. So relatively recently, but it was open for 280 years. Pretty amazing. So there are actually many other questions. Maybe sometimes we ask how, sometimes we ask what the bound is, or what is the highest, what is the lowest, etc. There are many, many other questions. notice that some of these questions may come from observations in the real world, but sometimes it isn't. Sometimes it's just for fun. Why? Because we are mathematicians. We like to play puzzles, right? I mean, why do you waste your time to play video games? For fun, right? Why do you want to like watch a television show? For fun. We need entertainment. We are human beings, and mathematicians' entertainment is to come up with new questions and try to solve them. That's indeed my pastime activities. Okay. Oh, yeah. So by the way, I skipped this point. Even if the questions come from the real world, we often was like, forget about the real world. We just want to abstract the problem. Now, why do we do that? There are a couple reasons for that. One of them is because very often, for example, if you talk about modeling or whatever, sometimes the real world is too complicated. And if you simplify a tiny bit, and you can get a rough model and understanding a lot easier. Other times, we want to abstractize it is because, for example, you look at a positive integer, you square that, and it turns out that it's positive. All right, so for example, 1 you square is 1, 2 you square is 4, 3 you square is 9. Oh, all of them is positive. So maybe you can come up with a conclusion that all positive integers, when you square it, it is positive. But you don't have to restrict to positive integer to start with. If you start with negative integers, if you square that, it's also positive. If you start with rational numbers, that means fractions, if you square that, it's also positive. If you start with irrational numbers like pi or √2, if you square it, it's also positive. So sometimes if you just focus just focus on one single problem and try to solve that because it comes from the real world, you might lose sight that, oh, the fact is why this holds is not because of this particular thing. It's actually there's bigger things behind it. So we want to abstractize it to make more observations all at once. Anyway, so to solve these problems, sometimes we need clever insights, but more often, I would say, it's actually just persistence and patience through messy work. I often say to my mentees when we do research, at the end of the day, is lots of dirty work. Yeah, like a lot of clean, nice theorems at the beginning, but when you look through the proof, it's tons of case studies or tons of like messy stuff. So many people say, oh, mathematicians are genius, very clever. Not really, they're just persistent enough. And mathematicians, we demand justifications for all our claims. We want to make proofs, and also we need to communicate precisely and concisely. That's why in my math courses, I always say, how do you present your ideas? That is very important to us as well. Okay, all right, so I realized I'm taking too much time a little bit. So let's try to get into one particular problem that I want to share with you. And I would like you all to think together. All right, so let me try to give you some background definition. It's very simple. So n, okay, no need to scare of it. It's just a positive integer. So n could be 5, n could be 17, n could be 24, just any positive integer. And s of n, just the sum of the digits of n. So not too big. So for example, if I've said 24, then 2 plus 4 is 6. That's what I meant. So 6 is the sum of the digits of that number 24. If the sum divides the number, then we call it an even number. This is the only definition that we need today. So just these 3 lines. So what happened is that, for example, 24 just now, right? If I try to sum the digits, is 2 plus 4 is 6. Does 6 divide 24? Can I have a show of hands? Yay, all right, good. So 6 does divide 24, and therefore 6 is an even number, okay? All right, so let's try to see more examples. Let's try to start with some small number, n equals 7. There are 7 days in a week, so why not? 7, the sum of the digits is just 7, am I right? Because there's only 1 digit. And so let me see, does the sum divide the number itself? Well, the sum is 7, the number is 7. So 7 does divide 7, therefore 7 is an even number. But it's just a 1-digit number. It doesn't give us much insight. So how about 17? The sum of the digits is 1 plus 7, so it's 8. And 8 is an even number. Even number cannot divide an odd number, correct? And so, okay, 17 is not an even number. 209, 2 plus 0 is 2, 2 plus 9 is 11. So is 11 dividing 209? And the answer is yes. How do I know? If you add 209 with 11, you get 220. 220, if you forget about the 0, is just 22. 22 is clearly a multiple of 11, and therefore your number is 11, multiple of 11. So that's how I see that. Okay, so 209 is also an even number. Good with this definition? All right, let's try to play with this problem now. Sorry. Okay, actually hide it. So pretend that you didn't see that. So we can just keep testing different numbers, right? So that would, to me, would be more like a homework exercise for grade, like middle school students or even elementary school students. But a mathematician will ask different questions. Is there any interesting questions that you can ask about these different numbers? How many? Very good. I like that. Knowing combinatorists, we always ask about how many, right? Or before we ask that question, you know what? Is there a largest different number in the world? Because if there isn't a largest, then the answer will be infinitely many, and we can't count them. Does that make sense? So the first thing is, are there infinitely many different numbers? Are there the largest one? So that's actually the very first question, mathematical question or mathematician question to come up with is, what is how many, or are there infinitely many? Okay, the answer is indeed yes. How do I see that? I'm going to provide you the answer. Rather, I want you to provide the questions, and I will provide you the answers. All right. Look at 1. 1 is a different because 1 divides 1. Look at the digit sum of each of these that I gave you. Isn't that all the digit sums are 1? Okay, the commas are separating the numbers. Okay, they're not like the position separated. Anyway, so for example, 10,000, the digit sum is 1. 1 does divide 10,000. So it is an even number, correct? Okay, so there are indeed infinitely many of them. We all agree. What next? What else can we ask about? Pattern. So for example, maybe they come in, well, actually before that, I did that again. This time it's even worse. Go back to the beginning of the slides. Somewhere here. Sorry. Sense. Oh, so before we do that, we probably want to ask, will it eventually be all even numbers? Does that make sense, right? I mean, if they are all eventually even numbers, then that makes even this concept not very interesting because they're just the same as positive integers, essentially. Make sense? Okay. And it turns out that there are infinitely many non-even numbers. These are non-even. How do I know? Because the digit sum is 2 for each of them. And 2 is an even number, cannot divide them. Great. Oops. What next? Yes. Nothing. Oh, I like that. Like, I mean, just basically the same thing as patterns or successive. Like, can we basically have them right next to each other in some, like, to start with, right? And so that actually prompts the next question. Are there any consecutive integers? I want greater than 10 because single digits, as you see, they are all even automatically. That's known. So anything bigger than 10 that are consecutive and even. It turns out that it takes a little while to find, but they're not too bad. It's 20 and 21 is the first pair, the very first pair. You can't do it in the teens. 2 plus 0 is 2, so 2 does divide 20. 2 plus 1 is 3 because whenever you sum the digits and it's 3, they always divide the number. There's a property of multiple of 3s. And so good, this is a pair. After knowing that you can get consecutive ones, what could be the immediate next question? Sure, we will hit that actually, but notice that I asked about, right? So maybe, is this just a fluke or will that occur infinitely many often, right? And so it turns out that they occur infinitely many often. And in fact, I'm lazy and therefore I'm used the same structure. How? Look at this. This is 20,000. The digit sum is 2. 2 divides that. The digit sum of this is 3 and 3 divides that. This is guaranteed because, as I said, it's a property of a multiple of 3. So good, there are infinitely many of them. And then now somebody already said, thank you, Dr. McLaughlin, about triples. Are there any 3 consecutive even numbers greater than 10? The answer is yes, you can do that, but it takes an even longer time to search for that, but these 3 will work. And can you get infinitely many of them? Yes, you can, like these. These 2, I mean, for example, some of the digits is 2, 2 divides that, some of the digit is 3, 3 divides that, so that's guaranteed to be a multiple of 3. This one is a little tricky, the sum is 4, but then it turns out that the divisibility test is just look at the last 2 digits. As long as the last 2 digits is a multiple of 4, then the entire number is a multiple of 4. And so this is also an even number. Okay, but now you feel a little bored. Why? Because that's what I meant, like, I mean, at the beginning, you can test different numbers. Maybe the first few are exciting, but then you get bored. And then maybe the first few interesting questions are interesting, but then you get bored. So what can you ask next? What are the interesting questions following this string of thoughts? Yes. Oh, the answer is no, I'm sorry. And I hit that again. The practical application is that you can get a paper published and have a very nice line on the CV. No, as I said, like so here is the thing. Very often practical applications may not occur right away. So for example, there's a French mathematician, I believe, his last name is Fourier or Fourier or whatever it is. And he did some analysis about sine and cosine functions, something that many people, many of our students hate, called trigonometry. And he just studied them and tried to approximate different functions using them for whatever reason that he just get interested in that. And then probably like 50, 60 years later, people found that denoising can use his theory. Yeah, like because different waves, if you have different wavelengths and different frequency, you can actually get rid of them by so-called multiplying or whatever it's called, multiplying some of the orthogonal waves, and then you will cancel them and get rid of them. And so very often we start with this just for fun. And then sometimes later you will find a practical application. And some of you may say, well, what if I just focus on those that have more potential and not those that have less potential? The thing is, sometimes the so-called more potential research is citing or based on something less potential. And so if you just try to cut it off right away at early stage, you will actually lose the opportunity to get to other things that might have a big potential in the future. And so in mathematicians' world, we just care about whether it's fun or not. We don't care about applications. Okay, any other questions that we can continue to ask along this line of thoughts? Yes, Mr. Thomas. Oh, you will eventually be Dr. Thomas, I'm very sure, but yes. Oh, that is a good question. I didn't prepare that. But that is definitely a good question. It's like you now know that there are infinitely many, but what is the density? That has to define it. And then actually there's somebody who did that. There's a paper published on that, but I'm not prepared for that on this, but very good one. Any other questions? Yes. Okay. I like that, right? After link 2, link 3, can we do longer and longer and longer or infinitely long? The answer, I mean, so here is our question. What is the maximum length of consecutive even numbers? Great, thank you for your question. And so we know for sure that you have at least 10 of them because these are all even. 11 is not even, so you cannot do that. But it doesn't necessarily mean that the maximum length is just 10, because maybe you can start maybe from the thousands, and then maybe somewhere you can get 11 of them or more. It turns out that I actually tried to run a computer program. It ran overnight, and then my computer gets hits up. And I think when I pause it, it was in the 900 million. And I still cannot find one that is length 11. But somebody knows the answer. The answer is, yes, you can actually make it longer. The longest one that you can get is 20. You cannot get more than 20. And but you can get infinitely many sequences that have exactly 20 different numbers. So after knowing this, then you can actually ask further questions, and those will be open questions actually. What is the first such sequence? It turns out that the currently known ones by Cooper and Kennedy has 2,000 digits long. So not 2,000, it's 2,000 digits long. And then somebody make it slightly smaller, 1,788 is what they can get. And that is the best known in 1997 by Wilson. And Wilson also showed that if you want to get such a sequence, it has to have at least 1,760 digits. It's guaranteed you have to have that at least that many digits in order to hit one. But nobody knows if there is anyone that is smaller than this 1788, but bigger than this. Okay, so if you are excited about this problem, go ahead and try. If you can solve it, you can definitely publish it in a very nice journal. Okay, I don't, how much time do I have? Oh, I don't have too much time. So I prepared this slide, but I think I'm going to jump over it. It's basically like to prove 20 is the maximum. It's a little more technical, but 21 is much easier. But still, I'm going to jump over that. Just a quick remark is that it turns out that the longest that you can ever get is these 21. Of course, 20 is actual bound, but it is very easy to see that these are the only ones. So what that means is that you're ending with a 90, ending with a 91, ending with a 92, all the way to ending with a 99, and then plus 1, then there will be a carry. So you have ending with 0, 0, 0, 1, all the way to 1, 0. That has to be it. And then it turns out that this one is not possible. We can do a little more work to rule this out and then get to 20. Okay. All right. So further investigation. So after knowing that, it sounds like everything is done, right? You know the density. Actually, somebody know the density. You know that there are infinitely many sequences of length exactly 20, and you know that you can't get more than 20. So what else can you do? It sounds like it's complete. But here is come the phrase, what if? What if we change the base from base 10 to base other things, right? And so Helen Grundman, in 1994 published a paper that actually studied the longest sequence in other bases. It turns out that the longest, for example, if you have base 6, then what is the longest one is the length is 12. If the base is 200, the longest that you can get is 400. Basically, it's 2 times of the base. And that actually generalized why 20 is the correct answer, because we are in the base 10 world, and 2 times 10 is 20. Okay, then after that, what else can we do? It seems like it's closed. And here comes this guy. So actually, I met with Helen right before everything shuts down in COVID. It was the conference was exactly 2 days before the announcement of COVID shutdown. And so I was really lucky that I attended that conference, and then Helen was one of the plenary speakers in that conference, and she talks about something like, related to this topic, and I got interested, and then I contact her because COVID, what else can you do? Do research, right? And so we actually start on working on that. We were like, you know what? Why do we just limit to ourselves to add 1 and find the next one? Because earlier I heard what is the pattern, or what's the distance between the next one, right? So what if I jump 2 steps? What if I jump 3 steps and just try to something called arithmetic progressions? So for example, 1, 3, 5, 7, 9, 11, that is called arithmetic progression with common difference 2, because if you subtract the consecutive numbers, you get 2. We actually get a lot of answers to that, but things are not as clean, because the answer, how long you can get, depends on both the base as well as what's the distance that you're talking about. But it turns out that for base 10, length 2, so if you just allow yourself to jump 2 numbers at a time, there are 2 types. One type is 137 1, 3, 5, 7, 9, 11, etc. So odd numbers, or you can have even numbers, 2, 4, 6, 8, 10, etc. So those are two types of arithmetic progressions. Both of them are jumping 2 steps at a time. The longest odd ones is length 10, while the longest even ones is a little unknown. We know that it's definitely between 10 and 13, but we don't know which case. So it's still open. And then we continue to work. How about we reverse the question? Look at all the jump size. You just start from any number and then just keep jumping. For example, I start from 393, and each time I'm adding 5 to it. Will I always guarantee to hit at least one even number? And it turns out that the answer is yes. No matter which number that you start with, no matter what the jump size that you choose, you will eventually definitely get to one of them. By the way, this is our notation to denote the years is because the paper is already accepted, but is waiting to publish. Mathematics journals takes maybe 2 to 3 years to actually from the submission to publication, and easily inside that 3 years, easily 1 year is just waiting between accepted and published. And so it's already accepted, but it's waiting to be published. Where am I? Oops, I'm close to the end. Yay, you're now free. Okay, all right, there you go. Okay, the next answer, the next one actually involves undergraduates. We investigated integers that are divisible by, instead of the sum, but by the product of the digits. But when you do products, you have to get rid of the zeros because, for example, 103, 103, 1 times 0 times 3 is 0, and 0 doesn't divide any integer. So that makes a lot of things not interesting. So we just look at the product of non-zero digits. And then the next one also involved undergraduates. We investigated integers relatively prime to the sum of its digits. So what that means is that instead of dividing, like for example, 6 divides 24, great. No, instead of doing that, we look at, for example, 17, the digit sum was 8. And then it turns out that 8 and 17 does not have any common factor. That's called relatively prime. And we study those instead. And there could be many, many more questions to come. And so that's my idea about this talk, is to share with you what I think of mathematics research is and what potential you can get through just playing, just trying to ask different questions. And before we go to the Q&A section, I would like to thank Dr. Lu for nominating me. Thank you for the committee for selecting me for this award. Thank you everybody for coming. I know that, for example, Dr. Coronto is on sabbatical and he purposefully stayed here to come to this talk. I'm very honored. Thank you, my wife. Like without her is impossible because I'm a lazy person. Everything at home is really taken care of by Jane, and without her, I mean, with your help is the only reason I could do things that I like and enjoy. So thank you, everybody.
We have one.
Dr. Wong, it's a comment, not a question.
Oh, okay.
Someone said that we don't care about application, about math. What the heck are you talking about? I do. Right?
Yeah. So no, thank you for your comment. Oh, sorry. Don't want to interrupt. So no, I mean, a lot of math is motivated by the real world observations. For example, the modeling or something called stochastic calculus, which looks crazy, but it's actually studying the stock markets. And why do they study the stock market? Is because they look at the Brownian motion, so-called, and then can find some math model to actually model some chaotic scenarios. So there are tons of math that has lots of applications and intertwined with other subjects. But what I meant is like mathematicians don't only study those. When we try to investigate very often the motivation or the key thing, why do we study that question, is not because of the application. It's not because I want to save the world. It's because it looks interesting to me. Or to that researcher. And that's really the motivation or the mentality of many mathematicians. Maybe you can say that they are irresponsible, they get paid and then they don't care about the world. But at the same time, it's like really just the nature of how many mathematicians think. It's like, do I get interested in that problem? Sometimes, I mean, for example, like there could be a very interesting problem out there, but even though it's very applicable, but you may look at it and say, this is not really my taste, right? So that really often happens. But thank you for your comment. Yes.
No.
Thank you, Maddie. I forgot your last name.
You blew my mind with your warm-up exercises. Can you
Thank you.
explain how you predicted everyone's missing number?
Oh, okay. Sure, that's not a secret. And actually, you know what? I would be very happy if you all can understand what's going on and actually show it to your friends. That would be really helpful. So what happened is that the number that I asked you to multiply by is called, anyone remembers that number?
387.
387, very good. So let's try to add up the digits. 3 plus 8 is 15. 15 plus, sorry, 3 plus 8 is 11. 11 plus 7 is 18. Because I'm actually using, I'm usually adding up the bigger digits first. So 8 plus 7 is what I have. It's 15, and then 15 plus 3 is 18. 18 is a multiple of 9. And because of that, the number 387 is guaranteed to be a multiple of 9. That is a property called divisibility property of 9. By the way, that only works for base 10. If you are talking about different bases, then you have to change it to other numbers. Anyway, whenever you start with a number that has a factor of 9 in it, then when you multiply to whatever number you have in your mind, that product is also a multiple of 9. Does that make sense to you? Okay, all right. So ahead of time, because I asked you to multiply by 387, even though I don't know what your number is, I know that it is a multiple of 9. And now what did I do? I look at your digits. I try to add them up, and they may be off because you miss one digit. And so all I need to do is to take the sum and find out what I need to fill in that gap to make a multiple of 9. So let me demonstrate that here. So for the first set, is 4 plus 8 is 12. 12 plus 10, because 3 plus 7 is 10, is 22. So 22 is not a multiple of 9, but I know that it has to add to something because there's one digit missing. It has to add to something to get to a multiple of 9. So what can that be? Well, 22, the next multiple of 9 is 27. And so I do 27 minus 22, which is 5. And that's how I get the answer. And so, Maddie, your number is this one? Or do you remember? Yeah, I remember this one. Yeah, exactly. 2168. So what I did was 6 plus 2 plus 1 is lucky. It's just 9. So I just forget about it because any multiple of 9, I can just forget about it. So I look at 8. What is the filler to make it a multiple of 9? And the filler is 1. Yeah, it's a very simple trick, but it can have a very good effect. Thank you for asking. Thank you, Maddie.
Why there are so many infinities in maths? You know, everywhere you touch, you end up with an infinity.
Yeah. One answer to that is because we are not afraid of infinity, I guess. We have like many ways to view infinity. In fact, we can classify different kind of infinities. We can say that some infinity is bigger than some other infinities. But of course, with the right setting and the correct language to really get that done. But what happens is that many people, when you don't have the right tools, then it's a messy concept. But when you actually lay it down, which will take a little while, but it won't take more than like maybe 2 hours to understand what we meant by the tools, and then you can actually understand what infinity is doing, and then we can handle that.
Does it relate to reality in some way?
Related to reality, I guess Not really. Like even for example, infinitesimally small, like infinite precision, you really can't get that. You can't get infinitely big, nor you can get infinitely like precise. So for example, if you want to know exactly what pi is to every single digits in the decimal representation, that's impossible because there are infinitely many of them. So in reality, much of it is approximations. For example, when we measure a length and I say that this is exactly 1 foot. Well, are you sure that this is exact? Well, this is probably not 1 foot. Maybe this is 1 foot. Is this exactly 1 foot or 1.0003467 foot? Right? I mean, so a lot of the real world application will be a lot about approximations. But like in mathematics, we kind of like what I said is we forget about the real world and make things simpler. Sometimes there are too many things that we can't control, and we just look at a skeleton and look at rough picture. Oh, that's roughly how it behaves, and then we can make applications to that. So infinity, there isn't too many things that approximate. Oh, but I did have to take it back. Actually, the concept, something called calculus, comes from infinity. So like you approximate a curve, and then you want to talk about the area under the curve. And what can you do? Well, there's no nice way other than just partition into small rectangles and try to measure the area of those rectangles and getting smaller and smaller and getting close to that. And so when you go to so-called the limits, then you can find the area. So there is some application in the real world, indeed.
How about the ideal world?
Hmm? Ideal.
Ideal world, yes.
What does that mean? Sorry.
The world, for example, you talk about.
Oh, ideal world. Yes, yes, I agree. Yeah, yeah. In the ideal world, that would be like infinite precision. Everything is there, but in real world, it isn't.
So why there would be so many infinities in such an ideal world?
I don't know. I mean, like because there's no bounds in integers. There's no bounds in the number of primes. There's no bounds to our imaginations. That might be the best way to answer your question.
Thank you.
Yeah. Yes, please, Dr. Back.
Hi, I'm not sure about the real world. Maybe you can help me out. If you have fractal shapes, don't you there have infinites in the real world because the scale of measurement can be made smaller and smaller or larger and larger.
Right.
And so then that seems to suggest that for instance, the circumference can be head towards infinity. That seems to me to be an example of an infinite structure in the real world.
Very good, very good. So fractals, just to make it clearer, is usually just some patterns that have so-called fractional dimension. So awkward, very awkward, because we usually talk about 1-dimensional, 2-dimensional, 3-dimensional objects. Even 4-dimensional is already complicated, let alone 1.23 dimension, whatever it is. So any object that lives in fractional dimension is called fractals. But fractals is not really abstract. For example, if you study the tree branches, okay, so without the leaves, you can kind of say that they are 1-dimensional, but they are not quite because they do cover quite an area, it seems, of the 2-dimensional space or 3-dimensional space, right? Even though each branch is just kind of like 1-dimensional. So you can see that that dimension is really between 1 and 3, but not quite either of those two. There's fractals have, many of them has repeated patterns. For example, if you look at the leaves and then if you scan through, I mean, just zoom through it, you will also see another kind of like small leaf inside or whatever. And so lots of fractals type of pattern occurring in the nature. But I have to say that those are approximations in the real, like from mathematicians' point of view, because we really can zoom in infinitely many and still get it. But in real world, once you zoom in enough, you will get quantum level and then you get chaotic and you can't study. But it is definitely kind of like have a taste of what infinity looks like.
Wouldn't another example be the n-body problem? Because you clearly cannot predict the orbits of planets. So you
Yeah,
have that.
chaotic.
And wouldn't that be because you have relations upon relations upon relations, you have an explosive domain there.
Yeah.
And isn't that a real structure?
Yeah, yeah. So n-body problem is definitely a very difficult problem. I mean, 3-body problem is already open. And so a lot of chaotic behavior there, I agree. Yes, Dr. Lem. Mhm, yeah. Oh, thank you. Right. Right. That's a very good question. I mean, so it's a very subjective question indeed. What is a good question or not? So a lot of it is really coming down to, does that arouse the interest of enough people? If like in the entire world, you are the only one who are interested in it, and even though you explain the concept to many, many other people and none of them are still interested in it, then probably we will say that that's not necessarily a good topic. But it doesn't mean that you shouldn't do it, because like there are mathematicians who try to do something that nobody understands it for maybe 20 years, 30 years, but then later on they found that, oh, wow, this is really amazing. They're just way ahead of the time of all the people. So that's why I say it's very subjective. After a while, it's really just not really a good or bad question necessarily. It's just whether it's interesting to you or not. So that makes it much easier. Now, try to be a mathematician. You don't need to worry about, is it a good question or not? Thank you, Dr. McQueen. You have a question? Hey.
So I just wanted to ask, what kind of research are you doing right now or recently? What are you interested in?
So right now, I mean, in the past week, I didn't do any research. I'm just preparing for this talk. Yeah, like I didn't even like go home until like past 1 a.m. last night, or this morning, you should say. Reasons, I mean, there are two problems that I'm working on with my collaborators. One of them is a graph theory problem, and the other one is something called zero-sum free, and that problem actually is shared with Mr. Thomas here. We have a REU project last summer, and it turns out that the question that we asked was, it seems to be easy enough that we can handle, but just answering any question, we have tons of questions, but this amount of answers. And so we are still looking for directions. Today, I actually came up with a little bit more when I was taking a shower. That's the best time to do research for me, is really when I'm relaxing and just doing nothing else, not interfered by the screens or phones, or well, I don't use my phone much, but computer screens, replying emails, when I'm just doing one thing, and then new ideas will come to me very often. So I encourage you to think about different things when you're taking a shower. You might be able to come up with the new idea for the next paper. Yeah.